Hello everybody. Welcome to the next lecture in the series of TensorFlow for Deep Learning tutorial series. And I'm going to take a slight digression today because as I was going through the lecture slides for lecture 5, which is what I wanted to make a video for, I saw that there is this one slide towards the early part of the lecture which shows a graph and just shows the backpropagation written out on there. And probably they explained it in detail in the lecture, but I could not find many slides on it. And I thought it's a really important topic to go deep into. And what I would try to do today is to give an intuitive description of what is happening when we think of backpropagation as a graph. So as you know, everything in neural networks, the reason neural networks are pretty much in vogue today is because of the fact that backpropagation allows the training of neural networks to converge relatively fast. And it is, even though frameworks such as TensorFlow really help in kind of not worrying about it, but I think it is very illustrative to understand it deeply at least once during your journey of deep learning research. So the way we'll approach it would be to start with the basic chain rule, and then we will put everything together in place to see how it fits into the whole backpropagation strategy. So if we were to do a very quick recap of what a neural network is supposed to do, let's say we are talking about supervised training at this point. So what we are given are all these training examples, x1, y1, x2, y2, and then let's say there are n of those, right? And the whole idea is for a neural network to find the function such that y is equal to fx, right? And neural networks by definition, well, not really by definition, but neural networks are universal function approximators. So theoretically, any function can be approximated by a neural network. And by the way, even a step function is a universal function approximator. But the whole thing is, one thing is theory, but practically whether or not you are actually able to find f, that is the whole issue. Now, this f, which is determining the actual output depending on the function, this is an empirical function and we might not ever get a handle on that. So the whole idea is, the trick is that we want to come up with a surrogate for f, which is g, which depends on x, which is input, and this is given, this is fixed, and some theta, which are the parameters, and we come up with an estimation y hat. And the whole thing we are trying to do is we come up with a loss, which is, let's say, a function of the y which is given and y hat. And if you were to look at what is under our control to kind of try and minimize the loss, we will see that j is a function of theta. The whole idea is that we want to minimize loss and j is a function of theta. So if we were to plot j as a function of theta, and let's say there is this some curve which is what we are seeing, what we want to do is to try to get to the minimum value of j, which is going to be somewhere around here, right? And the way we do it is, like, depending on wherever our theta is, we will go ahead and let's say we are somewhere here, right? We are going to find the gradient of j at that point with respect to theta, and then we are going to walk down. So we are going to change the theta so that the j goes in the direction that we want, and hopefully we are going to go to a minimum out here. Now, all that this method guarantees is that you are going to go ahead and hit some local minima. You are not guaranteed to hit this other minima, which is actually a better point for j, but there is no way to get to that. If you had started here, and that's where, when we start training our networks, all our parameters are random, so they can be anywhere, but once you get there, it's going to just move and get to the minima that it hits. So as is clear from this discussion, that what we are interested out here is finding the derivative of j, the partial derivative of j with respect to the theta, right? And this is the all important term that we are always seeking when we are trying to train a neural network. Because in the next iteration for the training, what you'll do is you'll update these theta parameters, so they will become theta new, which will be theta old minus this quantity del j by del theta, and there will be some alpha out there. And this is how you're going to be coming up with the new value of theta, and then you're going to see where you're in the curve, and you're going to keep on descending. So now let's roll all the way to the top, and let's go ahead and motivate the chain rule. One thing to realize in neural networks is that we are always doing numerical differentiation. We are not doing symbolic differentiation. So what that means is we always have values for the inputs. And we have our model, and we have a way to get to a scalar for loss, right? So we will always have certain values. So let's go ahead and put some values out here for x, y, and z. So here's the setup. We have some values for x, y, and z, and there is this function f, which is calculating x plus y into z. And what we would like to get is the partial of f with respect to x, with respect to y, and with respect to z. In our first very simple example, this is what we want to do, okay? And we can see that, let's say that x plus y we replace with q, right? So then we have q is equal to x plus y. And by the way, I am borrowing this example from Andre Karpathy's slides from January 2016 for CS 231 class that was taught at Stanford. So a lot of these numbers, some slides down the line that I'm going to be talking about are from that. So feel free to go ahead and look at those slides also. So we have our q, and at this point, f becomes q into z, right? So if we were to just look at the partial of q with respect to x, del q by del x is equal to 1, right? Del q by del y is equal to 1, and del f by del q is equal to z, and del f by del z is equal to q. So this is all pretty standard so far. Let's go ahead and fill in the values for the forward pass. So this is an addition, so 5 minus 2. So out here, q is equal to 3, and z is equal to minus 4. We are multiplying, so f is going to be minus 12. Okay, so this is the forward pass of everything. So from the graph perspective, let's see what we have. What we have are these values, which are the forward pass, and again, we are looking at numerical differentiation. The other thing we have are what we call the local gradients. So for example, we have del f by del q, right? So we have that, del f by del q. We have del f by del z, which is right here, because if you look at this circle as the operation, the output differentiated with respect to the input, we have that local connection. But what we need is the final output f with respect to the distant variable, which is x and y, and that's where the chain rule comes into place. So what the chain rule would simply state is that del f by del x, which is the distant variable, is equal to del f by del q into del q by del x, right? So this is the chain rule that we all learned in high school, and I wish we had, instead of doing a right multiply of this, if we had done a left multiply, then it would have generalized better to matrix chain rule, but we'll talk about that in a little bit. So now to find the gradients, we just imagine a backward flow of the gradients from this point onwards. So out here, del f by del f is going to be trivially 1, right? So this is the very last output node, and we are doing del f by del f, right? And this is trivially 1, so we write the gradient at the bottom of the line as 1. Now, del f by del q is going to be this part, which is the local gradient that we calculated, del f by del q, multiplied by whatever is coming in as the gradient, which is 1. Okay, so again, del f by del q out here is z, and z is minus 4 multiplied by what is coming in, which is 1. So we write the gradient out here as minus 4, and now this gradient is going this way. Let's look at z out here. So del f by del z is q, okay, and which is the value 3 multiplied by the gradient which was coming in 1. So this is 3, and this is the gradient going in this direction. Now let's look at the x branch out here. So out here we have the local gradient, which is del q by del x. We already calculated that to be 1, right? And then we have this minus 4 flowing in, so that's going to be 1 multiplied by minus 4, and that's going to be the gradient out here. And since the direct connection, we have minus 4. Okay. Now with y, similarly, we have del q by del y is 1, and then we have minus 4 flowing in, so 1 multiplied by minus 4 is here. And lo and behold, this 3 is already here. We have all the values, del f by del x, del f by del y, and del f by del z. All of these 3 are now here, and that's what we, well, this is not z, this is 3. And this is what we set out to calculate. The important thing to keep in mind is that we are always calculating the gradient with respect to the final loss function. So in a neural network, this f is going to be that j, the loss function j, right? And everything that we are calculating is going to be with respect to that. So it's always going to be del j by del w1, etc., etc. So that is an important point to remember, because that's the only thing we really care about. If you were to zoom in as on what a neuron in a neural network is actually doing, by the way, I'm feeling very proud of myself that I was able to figure out a way of creating these basic shapes in the program that I'm using on my iPad for this recording. So anyways, so what the neuron does is that it is getting these inputs at any point, right? And it knows a function that it needs to calculate, and it goes ahead and calculates that. And this function can be very simple, anything, right? X into y, or w into x plus w1 x1 plus w2 y2, whatever. And it will get its z, it will find the output z, and it will send z over. Right, so that is one part of that's what it's doing during the forward inference part. And right here, it's simple to see that we can easily calculate our local gradients. So if we have this function as w1 x1 plus w2 x2, then del z by del x is w1. We can locally calculate it very simply, and we can have it available for us. During backpropagation, what will happen is right here, we will get in this direction this time del j by del z. So this is something you would actually just get. So if you were to write a backward function for a neuron, in the argument would be this del z, which we usually call it like dz, but what that means is del j by del z. So this is something that you will get, right? You will have that available as a number. And you have these things, del z by del x and del z by del y. So what you would do is now you will multiply this number, which whatever you get, del j by del z, you'll multiply that by this local gradient, and which is going to be, well, let me just multiply it on this side, del z by del x, and you will send it over in this direction. Similarly, out here you will get the del j by del z multiplied by del x by del y, and it's getting sent over in the opposite direction. So whatever neuron, if there are other neurons out here, let's say that are sending x over here, then what they get out here in the backward flow is del j by del x, which is their output. The output of this neuron is x, remember, at this point, and now it's getting it in this direction, which is the same thing that we are looking at out here. So this is going to be that symmetric view where the gradients are flowing in the opposite direction. Now let's see how we can use the same graph computation technique for calculating the gradients when the function is a little bit slightly more complex than the simple addition and multiplication we were looking at. So this is the sigmoid function, and let's see how we can calculate the gradients out here. And here I'm laying out the full computational graph, and I'm starting with some values of W0, X0, W1, X1, and W2. And basically the values that you see out here are just the forward pass, where out here 2 multiplied by minus 2, minus 3 multiplied by minus 2 out here for W1, X1 is 6, added minus 3, we are getting this, multiplied by minus 1 for this one, and we are getting minus 1.0, exponentializing that, 0.37, adding 1, 1.37, 1 by x is f is equal to 0.73. So this is where we are calculating the forward pass, and again numerical differentiation is something that we are going to be looking at for the backward pass, so we always have a number to work with. So now let's start calculating the backward gradient. So del f by del f trivially out here, and we'll be writing the gradients below the line. So del f by del f is 1, so we get that here trivially. Now when we look at this node, the function being computed is 1 by x. So whatever the x is out here, the function is 1 by x, and if you were to look at fx is equal to 1 by x, so del f by del x is equal to minus 1 by x squared. So that's going to be the local gradient. Okay, del f by del x is minus 1 by x squared. The value of x is minus 1 is 1 by 37. So what we are going to be calculating is minus 1 divided by 1.37 squared. Okay, and that multiplied by what the gradient flow in this direction, which is 1 at this point, is going to be the gradient here. So this value comes out to be minus 0.53 and multiplied by 1, which is coming. So out here we have the value minus 0.53. So this is going in this direction at this point, right? Okay, so this is a plus 1 out here, So the function we are looking out here is fx is equal to 1 plus x. So del f by del x is equal to 1. Okay, so that's the local gradient. And what is coming in the direction, in the opposite direction, is minus 0.53. So 1 multiplied by minus 0.53 is something we'll write out here, 0.53, and there is a minus in front of it. We look at the next gate. It's an exponential function, so fx is equal to e raised to x. Del f by del x is again e raised to x. So del f by del x is e raised to x, and the value of x out here incoming on as the input to this gate is minus 1.0. So what we want to calculate is the local gradient is e raised to minus 1.0, and what is coming in is minus 0.53 multiplied by minus 0.53, and what we get out here is minus 0.20. So we have minus 0.20. Apologize for the handwriting out here. It's I should have made the graph a little bit bigger, but this value is minus 0.20, and it's moving, and again we are going in this direction. For the next gate out here, the function is fx is equal to minus x, and del f by del x will be minus 1. That's the local gradient. Minus 1 multiplied by minus 0.20, so we have 0.20 is the gradient out here. Now when we look at the add gate, the function out here is fx is equal to whatever this is, x plus y out here. And if we were to do del f by del x, when we are looking at this branch, it's going to be 1, right? So the local gradient with respect to this input is 1. And then we have 0.20, so 1 multiplied by 0.20, we will have 0.20 going out here. Exactly the same argument out here, x plus y, del f by del y, 1 multiplied by 0.20. So for W2, we already have the del f by del W2, we already have it as 0.20. Okay, now let's see what's happening out here. Again, out here we are seeing another add gate. So x plus y del, it's going to be 1 for the top branch. 1 multiplied by 0.20, we write it 0.20 out here. Similarly, this is 0.20 for the bottom branch. Now, if we look at the last multiplicative gate, what the function out here is, whatever is coming out here, let's say this is, if this is x, this is y, then the function is equal to x multiplied by y, right? So if you were to do del f by del first input, which is x, it's going to be the y, which is going to be the other input. Okay, so if we were to look at the top branch out here, the local gradient is the bottom input, which is minus 1.0. So the gradient is minus 1.0 multiplied by whatever is coming in, 0.20. So we write it 0.20 multiplied by minus 1. Similarly, the same exact argument for the bottom branch, the gradient, the local gradient is going to be the value of the top input, which is 2.0. So we multiply 2.0 with whatever is coming in, which is 0.2. So we get 0.4, which is the gradient of the bottom branch. So finally, out here also we now have del f by del x0, and here we have del f by del w0, and this is what we wanted to calculate. Now the only branch which is remaining is the last one, exact same argument that we saw in the top multiplicative gate, where if we were to calculate the gradient for the top branch, we are going to take the value of the bottom branch, which is minus 2.0, multiply it with that's the minus 2.0 is going to be the local gradient, and once we multiply it by 0.2, it's going to be minus 0.4. And if you were to look at the bottom branch, it's going to be 0.6 with the multiplication, so minus 3 into say 0.20. At this point, we have all the gradients that we seeked. So you can already start seeing some patterns where when we are trying to calculate the backward flow, if you hit a AND gate, the gradient is just going to get distributed. So exactly, it's going to get replicated, right? So 0.20 was the one coming in. There's an AND gate, and and what we see out here is 0.20 for the top one, 0.20 at the bottom one, right? If it's a multiplicative gate, what we are going to get is it's going to switch. It's going to switch and multiply. So basically, whatever is coming in, and if you're looking at the top branch, you look at the input of the other branch, multiply by that, and that's going to be the gradient of the first branch, and similarly for the second branch. So this is a pattern that you can remember, and it's very easy to see. Even if you forget it, you can just like really get to it very fast, and you can use it for calculating your backward flow. One thing to notice is that if we are seeing branching, for example, a function is getting calculated, well, let me just make sure that I don't overwrite on myself. If a function is being calculated and the output is branched into two different nodes, right? Now what will happen during the backward flow is, let's say out here something happens and then we finally do end up getting to L, right? So if you look at just the top branch, right, this calculation, what will come out here is a del L by del Z, right? And for the second one also, we will have del L by del Z, and these will in general be different values. So what we will do is we will be adding up the gradients at this point. When we backpropagate those gradients, we would have the local gradients out here, and then we will multiply that local gradient with a sum of these two, and then that is the value that's going to be passed on out here. So from a computation perspective, all we need to do is for each of these gates, be it a addition gate or a multiplicative gate, what we want to do is to define a forward function, right, and a backward function. Okay. The forward function will take some inputs, let's say x and y, and will return, and this is just pseudocode, the function that it's calculating, in this case x plus y. And the backward function is going to take in input which is coming from the back direction, which is going to be the dz, and now it's going to be multiplying the dz with the local gradient. So in this case, for the local gradients with respect to x is going to be 1, and it multiplies by dz, it's going to be dz. Similarly for y, the local gradient is 1 multiplied by dz, it's going to be the dz, right? And it's going to return this on. And the beauty of this thing is that once we define these forward and backward functions for each of these gates locally, now no matter how complex your computational graph is, all you need to do is to do a topological sorting so that of the nodes, so that we have the ordering from the inputs all the way to the outputs, and the last node is going to calculate the loss. So we just go ahead and chain everything together. So if this is the case, then for the first one, we'll calculate the forward for this, and then whatever the output is, that's going to become the input for the second node. We are going to do again the forward on that, all the way to the loss, and loss is going to be the thing that we are going to be returning as the final total of the all the forwards chained together. And then what we are going to do is, for the backward pass, we will have the DZ, the initial DZ. Remember when we did the del J by del J, or the last thing was 1. That is going to be the place at which it starts for the very last node. And then it's going to make all these calculations, and it's going to keep on sending the stuff in the other direction. So the whole idea, and that's where, when we were going through the TensorFlow architecture, and the entire thing is setting up the computational graph, and there is this is the reason why things are done in this way, because this the whole backpropagation, when you look at it as a computational graph, it just falls into place very nicely. And the next thing to consider is how we will deal with the situation when x, y, and z are vectors, and this is what you'll probably be seeing most of the time when you are trying to do anything with neural networks. So when we are dealing with vectors, and if you try to differentiate del z by del x, and let's say z is a 3 by 1 vector and x is a 2 by 1 vector, then the way we do this result, del z by del x, is the Jacobian, right? And its dimensionality is going to be 3 by 2, and basically what you're doing is take each of these z's and differentiate by the first element, which is del x1, del x1, del x1 out here, and do the same for the second element of x2. So this entire matrix, this entire Jacobian matrix, is this part, is what we are calling the local gradient. Similarly, we'll have another local gradient for y, which is again going to be another Jacobian matrix. If you look at the gradients flowing from the other side, del L by del Z out here, that is going to be a row vector, which is going to be del L by del Z1, del L by del Z2, and del L by del Z3, if we are looking at Z as Z1, Z2, Z3. Okay, so this is going to be flowing in on this side. Now, the chain rule for when we are looking at vectors and matrices, etc., in general, the chain rule is going to be as such. If we were to look at this top branch out here, we are going to left multiply this Jacobian matrix. So again, del z by del x is this entire Jacobian matrix, and we are going to left multiply it by whatever is coming in out here. So what we are going to do is del L by del z, and then del z by del x, and this is going to give us del L by del x. And this is going to be going in the other direction. And what we'll see is out here also, del L by del x is, if you just go through the left multiplication, there is a row vector on the left side, and then we have this Jacobian. If you just quickly go through it mentally, you'll see that del L by del x is going to be another row vector, which is going to be del L by del x1, del L by del x2. Okay, and this is going to go similarly out here. For y, we'll have del L by del y is equal to del L by del z into del z by and this is going to be another row vector which is going to go in this direction. Let's take a look at an example from a computation perspective as to how we can really go ahead and stage the computation of the backpropagation. So let's say, for example, we have this function xy, which is x plus sigma y divided by sigma x plus y squared. Now, sigma is the sigmoid function, and one of the things that we should keep in mind is that sigma dash of x is equal to sigma x multiplied by 1 minus sigma x. So you can convince yourself that this is true, and we are going to be using this as we go through the computation. Let's go ahead and calculate the forward pass. So if we were to start with values of x and y, 3 and minus 4, what we want to do is to create all kinds of intermediate variables, because we don't really need to symbolically come up with a differentiation for f with respect to x and y. We just need to tell the computer as to how to use it, okay? So by keeping that in mind, things become relatively simple. So for the numerator, we define a variable sig y, which is 1 by 1 plus math dot x minus y, which is the definition of sigmoid. The numerator would be x plus sig y, and sig x for this value is 1 by 1 plus math dot x e raised to minus x. X plus y is x plus y. X plus y squared is this value raised to 2. Denominator is this plus this. And the inverse of the denominator is 1 by denominator, 1 by den. And the final function, the forward pass, the last value, is numerator into inv den, right? So at this point, we have the value of the function, and we are ready to start doing our backpropagation. So just some notation, everything that we want to calculate is going to be with respect to f, right? So basically, when we look at now for backpropagation, we start with the very last statement, the f is equal to num into inv den, and we want to start calculating the gradients, right? So as a matter of notation, when we say, if we wanted to write del f by del numerator, we can just write this as dnum, because it's assumed that everything is with respect to f, right? So if you look at this function, let me just change the pointer. If you look at this gate, then the input is num and inv den, and this is the output. So when we calculate the gradient with respect to the input, which is del f by del num, which we are calling it dnum, then it's going to be this value inv den multiplied by whatever the output gradient is, which is going to be del f by del f, which is 1. So we get out here. And similarly, for the other input, which is to this gate, which is inv den, we would say d inv den, which is equal to num, right, and multiplied by del f by del f. This is the very first well, it's number 8, which is the last but the very first calculation in the backward pass. So we are here. We are done with this gate. Now we look at the gate before. So this is the output, and the input is den, right? And we want to calculate the local gradient, which is going to be d10. d10 is going to be minus 1 by den square. So d10 is equal to minus 1 by den square multiplied by whatever the output was, and the gradient of f with respect to that, and which we are defining as dn. So this minus 1 by den square multiplied by dn, and we are done with number 7. Now we go ahead and look at the one before. Again, out here, if we calculate with respect to d sig x, is going to be xpy square multiplied by d10, which is this is well, d d sig x is just going to be 1, and this is going to be 0. So 1 multiplied by d10, which is what we are seeing. And similarly, the gradient with respect to this is going to be the same, right? Because it's a multiplicative gate, and the gradients just go ahead and distribute themselves. Okay. Xpy square, we calculate with respect to dxpy is equal to 2xpy multiplied by dxpy square, and that's what we see. And we will probably need to scroll up a little bit. Okay. dx out here is going to be 1 multiplied by dxpy. dy is the same. And if we were to scroll up, when we look at this sigmoid function, sig x is equal to 1 by 1 plus math x minus x. Now we see the input is x, so we now do dx, but we see that we already have dx out here available. So what we do is now branching is happening at this point. So instead of equal to, we are not going to just go ahead and override this. We are going to be doing plus equal to, right? And that's the interesting part, because sometimes when you are thinking of branching and whether the gradients get added or what's happening, it might get confusing. But pretty much when you're staging the computation, it almost just falls to you, because you see that you have already used dx out here, and again we need to, that's variable comes up again, and whenever that happens, pretty much you just need to do a plus equal to, right? So what you'll do is, we said that sigma dash x is equal to sigma x into 1 minus sigma x into d sig x, and all d sig x, we already have this value calculated somewhere right here, right? So and this is exactly what makes this thing so intuitive, as you just go backward through all the functions, and you can go through the rest of them. They are pretty much the same functions, so we don't need to be repeating ourselves here. And again, you'll see the dx coming up again. At this point, we are again going to be doing a plus equal. So whenever there is this branching happening, you are going to be adding the gradients, and when you're staging the computation this way, you'll see that this just falls out. And finally, we have dx and then dy, and this is what we started with. The goal was to calculate del f by del x and del f by del y, and this is what we have. And in addition to that, we have the gradients for all the intermediate steps. And the final thing I would like to cover is how to take care of the gradients for vectorized operations. And in this case, we are going to go take a look at the matrix multiply. So let's just look at the example. Let's say we have a matrix W, which is 5 by 10 np dot random, and there is a x input, which is 10 by 3, and we calculate the forward pass, which is d, is w dot x, right? So the dimensionality of d is going to be 5 by 3, right? This is going to be the dimensionality of d. Okay. Now, let's say we have some j and we have del j by del d, which is coming in from the top, and we have that. So using our previous definition, this term we are going to call it as dd, which is what we have out here. And let's say we have this some number that's coming in, and obviously this the gradients will be of the same shape as the actual value. So because we are taking the gradients with respect to a scalar, and we will let's just come up with some matrix out here which is the same shape as D, which is going to be 5 3, right? Okay, so now if we were to go ahead and calculate, if so for this function the inputs are w and x and we are calculating d, right? So if we were to calculate with respect to w dw, now we know that it's going to be some dw is equal to, well, first of all, if we were to do this del d by del w, it's equal to x, right? And now we want to calculate it with respect to j, so we are going to be multiplying with dd. So now the confusion arises as to how we take care, what do we do to make sure that the dimensionality works out. So it's usually what you want to do is, you know the dimensions of W, which is 5 by 10, right? And you know the dimensions of DD, which is 5 by 3, and there is going to be and you know that like you have to multiply this by x. So there is going to be only one way that once you do the transpose dot etc., that these dimensions are going to work out, right? So you can either remember this thing that and probably a good idea to do that, because you'll see this w dot x a lot of times, so might as well just remember it. But if you don't, then you know that, okay, well, there is only one way that this dimensionality will work for dw, and dx also it's pretty similar, where it has to be w into some into dot dd, and the actual thing is w dot t, which is the transpose, and you do a dot product with d. So this is pretty much the same and generalizes pretty well from all the scalar discussions we had on gradients, but this is something that you'll run into quite a bit. So hopefully this gives you a good understanding of why we think of why we are doing all these computational graph operations in TensorFlow. And also, even though a lot of this, pretty much all of this complexity is completely abstracted away when we use frameworks such as TensorFlow, where there is auto differentiation and everything. But I do think it's important to get a feel for what is happening under the hoods, because you might come across a situation where you'll have to write your own layer, and this is happening for one of the projects that I'm leading at work also, where we need the layer that we need to use is not there in TensorFlow, and we need to actually code up the layer and the forward and the backward passes. So having a good understanding of this is really, really useful once you start using stuff which is outside the standard library. Thanks a lot.